Okay, today we're going to look at finding zeros of polynomials when they're in standard form. So first we're going to recall how we find zeros in factored form. And just review that quickly. And hopefully we'll see why that's the superior form for this, for finding zeros. So if I wanted to find the zeros of this polynomial, we'll say x plus 2 times x minus 5 times 2x minus 3. So we know there's a couple ways to do this, but some of us know that you just take the opposite guy here. So like for x, the factor x plus 2, we're going to say x equals negative 2, and for x minus 5, we're going to say x equals 5. And then for 2x minus 3, it's not so easy, so we can use the other way we think about this is we want this factor to equal 0, so we write that. So we write 2x minus 3 equals 0, and we're going to find the x that forces that entire factor to be 0. So we add 3 to both sides, divide by 2, and we find out that that is 3/2. So those are our zeros. That is how we find them in factored form. Remember, they're called zeros because they are the x's that when I plug them in, they make y equal 0. So another way to write them also is as points, which really stresses that they're also x-intercepts. Like I could write negative 2, 0, 5, 0, and 3/2 0. I like this because it really reminds us that these are the x's that produce a 0 for y. We can check that that actually is the case, and this is going to be the important piece for today. So normally we just did it to be sure of our answers, but we're going to actually use this check today to our advantage. So I'm going to review how did we check that these are zeros. Well, we would take those answers, like say negative 2, I'm going to check that x equals negative 2 is a 0, and plug it back into the factored form. So I get negative 2 plus 2, whoops, put a comma there. Negative 2 plus 2 times negative 2 minus 5 times negative 2 times negative 2 minus 3. So notice that I just went for all the x, wherever x appeared, I put negative 2 in its place. So if I simplify that, I get 0 times negative 7 times negative 7. That indeed equals 0. It checks out. Let's check that x equals 5 is a solution. So I get y equals, I'll plug in 5 everywhere for x. So I get 5 plus 2 times 5 minus 5 times 2 times 5 minus 3. So when I plug in 5 everywhere for x, I get 7 times 0 times 7. So again, we notice that if any one of these factors becomes 0, the whole product equals 0. That's the zero product property. So that is also a solution. And then we can finally check that 3/2 is a solution. You can see that negative 2 made the first factor 0. 5 made the second factor, right? When we plugged in negative 2, we got 0 on the first factor. 5 made the second factor 0. So it looks like 3/2 will make that third factor 0. So x equals 3/2, we're checking that one. So we get y equals 3/2 plus 2, and then 3/2 minus 5, and then 2 times 3/2 minus 3. 3/2 plus 2, I don't feel like adding fractions, but who cares? It's some number. It's not 0. The second factor, 3/2 minus 5, I don't feel like doing that one either. So that's just some number. Again, who cares? It's not 0. Why don't we care? Because this last one should be 0. 2 times 3/2, we do have to do that even though I may not feel like it. 2 times 3/2 is 3. So then I have 3 minus 3. So then I get a number times some unknown number times 0. And all that matters is that 0 because that makes everything 0 by the zero product property. So we just proved or checked that all three of these are indeed zeros. That's going to be very important today. All right? So let's move on and work on finding zeros in standard form. So this is the goal for today. That was a little review. Now we're going to look at finding zeros in standard form. And we'll see why factored form is definitely preferred. Standard form, this process we're about to learn today, it's a little bit lengthy. So it's much easier to do what we just did there when it's in factored form. So first of all, we will use a theorem called the rational zeros theorem, or the rational roots theorem. So the rational roots theorem. And I'm not going to tell you what that theorem is right now. We're going to kind of do that at the end of this lesson. I do want to tell you that this theorem can be super cool because it is easy to apply and use. So that's what makes it pretty cool. It's easy to do. I can come up with the answers pretty quickly to what it's trying to tell me. The theorem, though, is not cool because although it gives me some answers, it will not give me the final answers. So it is not cool because it will not give me the final answer. So remember, we're using this to try to find the zeros of the polynomial. So what this theorem does is it says, hey, I can tell you that it's one of these 10 or 3 out of these 10, but it doesn't tell you what they are. So you got to figure that out on your own. But it is nice because it narrows down the list to say 6 choices or 8 choices or 10 choices, and then we have to go from there. All right, so we're going to look at how we use this theorem. So the first thing that we're going to discuss with this theorem is it's called the rational roots theorem. First, let's recall what is a rational number. It's important to understand this. It'll help you remember the theorem. Okay, so a rational number, if we look back to our zeros that we got earlier in that example, we got -2, 5, and 3/2. These are all rational numbers. So a rational number is any number that can be basically expressed as a fraction. 2 over 3, 5 over 1, right? 7, because that could be 7 over 1. As long as the numerator and the denominator in the fraction are both integers, it works. Let me give you some examples of things that are not rational. Like square root of 3 over 2, yes, I can express that number as a fraction, but square root of 3 is not an integer. Therefore, that is not a rational number. All right, pi over 2. That is not a rational number. Yes, it's expressed as a fraction, but those are not integers. Pi is not an integer. So again, any fraction where the top and the bottom are integers are okay, and even whole numbers are okay because I can always write them as over 1. So that's what a rational number is. It's important to think fraction here for a rational number because that will tie into our theorem, okay? It'll help with remembering how to do the theorem. So that's what a rational number is. The second thing we have to look at is if the theorem does not give us final answers, the final answers for the zeros, does not give us the final answers, then what the heck does it give us? Again, we're not going to use it yet. We're still trying to figure out just how it works. So for example, let's say we have the polynomial y equals x cubed plus 3x squared minus 4x minus 12. Let's say I ran the theorem on this polynomial. You don't know what it is yet, and it came up with these: -1, 1, -2, 2, -3, 3, -4, 4. It said, hey, these are your possible zeros. I mean, that's cool because before that, our possible zeros were all the numbers in the universe. That's a pretty large amount of numbers. So at least it's narrowed it down to 8 possibilities now. Theorem is not cool because we got to figure out which ones are actually zeros. So how are we going to do that? We have to check each one of these by plugging it back in to the polynomial and seeing if I get 0. So remember, that's what we did here, right? We checked. Plug in -2 and see if we get 0, but except this time it's not in factored form. So let's do some checks on this. So first I'm going to check the possible 0, x equals -1. So if I plug that in, I get y equals -1 cubed plus 3 times -1 squared minus 4 times -1 minus 12. I get -1 plus 3 plus 4 minus 12. So I just did -1 cubed, right? This means -1 times itself 3 times. -1 times -1 times -1 gives me -1. -1 squared gives me +1, and then times 3. So that's how I got the 3. -4 times -1 gives me the +4, and then the minus 12 just carries down. So now I've got y equals 3 minus 1 is 2, plus 4 minus 12. That equals 8 minus 12, -4. So it is not a 0. -1 does not work. So rational roots theorem, thanks for the chance for it to be -1, but that's no good. I'm going to tell you that 1 also doesn't work. I've already kind of worked these out. So you plug in 1, it doesn't work. So we're not going to waste our time in the video doing that. Does not work means you will not get 0 for a final answer for y when you plug in that, right? So I should write it this way, -1, -4. That means that would be a point on the graph. We can clearly see that's not a 0 because the y is not 0. All right, let's check one that works. It looks like 2 works. So if I plug in 2, I get y equals 2 cubed plus 3 times 2 squared minus 4 times 2 minus 12. So let's see here. 2 times 2 times 2, that's 8. 2 squared is 4. 4 times 3 is 12. This is -8. This is minus 12. Whoops, got the eraser. Right? -4 times 2 is -8, and then I have the minus 12. This does equal 0. So the point 2, 0 is on the graph. That means x equals 2 is a 0. We have a winner. Now, what is nice to know is we learned that if it's a degree 3, it can have up to 3 zeros. So you could know when to stop. I got 1 already. We only need 2 more. So if you get 2 more that work, you can stop. You don't have to check all of them. Okay, so it can have up to 3. It doesn't have to have all 3. That's another thing that we're going to talk about in this topic, in this unit. So we would just keep testing off this list and see which ones work. So let's try -2 and see if that works. So we're going to check x equals -2. So I get y equals -2 to the third plus 3 times -2 squared minus 4 times -2 minus 12. -2 to the third is going to be 2 times 2 is 4 times 2 is 8, but it's going to be negative because those are all negatives along the way. -2 squared is 4. 4 times 3 is 12. -4 times -2 gives me a +8, and then we have a minus 12. That indeed does equal 0. So -2 is also a 0. All right, so there's only one left that could work. Let's try one more. I would like to try -3. Let's see if that works. Check. Actually, let's do +3 first. X equals +3. So y equals 3 cubed plus 3 times 3 squared minus 4 times 3 minus 12. 3 times 3 is 9, and then 9 times 3 is 27. 3 times 3 is 9, and then 9 times 3 is 27. This is -12. This part is -12. This is 27 plus 27 minus 12 minus 12. That does not equal 0. I'm not going to work out what it does equal because I just want ones that equal 0. So +3 is not a 0. We have to carry on. Let's check -3. We get y equals -3 cubed plus 3 times negative 3 squared minus 4 times negative 3 minus 12. So negative 3 times negative 3 is 9, times another negative 3 is negative 27. Negative 3 times negative 3 is 9, 9 times 3 is a positive 27. Negative 4 times negative 3 is a positive 12, and then we have our minus 12. These equal 0, those equal, so indeed this one works, it equals 0, and here's where your knowledge of polynomials will really help. You don't have to test negative 4 and 4. This was a degree 3, and we know that degree 3 can have at most 3 factors, at most 3 zeros. We found 3 zeros, we're done. Those are our zeros. So the zeros are x equals negative 2, 2, and negative 3. All right, so that's great. That's all well and good. We had to check all of these, and we see now how we can check from our list of possibilities. The final question we have to answer today is, how do we use that theorem to come up with the list of possibilities? So we're going to finally get to the theorem, and that's part number 3. How can we use the rational roots theorem to make a list of possibilities? So the theorem says that if you have a polynomial in this form, actually we'll go Q. Yeah, I like P first. I like to do it backwards. All right, P x to the n plus dot dot dot. So x to the n is your highest power. So this is a polynomial of nth degree, meaning the n is the highest power, all the way down to your coefficient, your constant. That's the one that doesn't have an x in it at all, and then we're going to call that Q. So this is our leading coefficient. Remember that the numbers in front of x that we multiply by are called coefficients. The leading one is the big dog. It's the coefficient for the highest power of x. And then the last one that doesn't have an x, that number, where it's just a number, that's called the constant term. So that's what we're really focusing on here. We're going to take the list of possibilities is you make all possible fractions from the factors of Q divided by the factors of P. So we can write it like this: factors of the constant divided by the factors of the leading coefficients. Okay, let's do an example. So if we have y equals 2x cubed plus 3x squared minus 2x minus 3, and our goal is to find all the zeros, we have to first start by making our list of possibilities. And we use the theorem for that. That is what the theorem says. It has nothing to do with the checking part. It's just making this list. That's it. End of story. So I take the factors of the constant, 3, and divide by all factors of the leading coefficient, which is 2. I don't worry about addition or like the positive or the negative. We're going to do all the combinations of that. So the factors of 3 are the numbers that divide into 3 evenly. 1 divides into 3, and 3 divides into 3. Now the factors of 2, 1 divides into 2, and 2 divides into 2. So now I make all my combinations of those factors. So I'll take the 1 first, and I'll make fractions with everything on the bottom. So I got 1 over 1 and 1 over 2. Now I'm going to take the 3 and do that. Make 3 over 1 and 3 over 2. Make all my possible fractions. So there's 4 possibilities here. I'm going to rewrite them. 1 divided by 1 is 1. 1 half I'm going to leave as 1 half. 3 over 1 is 3, and then 3 halves. And then I've got the positive and negative version of all of those. That's why I don't have to worry about paying attention to signs earlier. So that means that I have 8 possibilities for zeros. Some people like to write them out like -1 and 1, -1 half and 1 half, -3 and 3, -3 halves and 3 halves. We got to check all of those by plugging them in. So let's start with -1. I'm going to rewrite the equation here. Y equals 2x cubed plus 3x squared minus 2x minus 3. So we're going to check x equals -1. So I get y equals 2 times -1 cubed plus 3 times -1 squared minus 2 times -1 minus 3. All right. -1 times itself 3 times is -1, and then times 2 would be -2. -1 times itself twice is +1 times 3 is 3. -2 times -1 is a +2, and then minus 3. That indeed equals 0. So x minus 1 is a 0. I'll start making my list. It said to find the zeros, right? X equals -1. This is our answer. How many will it have? It can have up to 3. So there's our first one, -1. So it was good. Let's try 1. X equals 1. If I plug that in, I get 2 times 1 to the 3rd plus 3 times 1 squared minus 2 times 1 minus 3. So this will be 1 cubed is 1 times 2 is 2. 1 squared is 1 times 3 is 3. -2 times 1 is -2, and then minus 3. That also indeed does equal 0. So 1 is a winner. We only need 1 more. All right, so we'll put that in our list for our answer. Okay, so the next one that we'll try is -1/2 here. We'll just kind of go in order. X equals -1/2. So I get y equals 2 times -1/2 to the 3rd plus 3 times -1/2 squared minus 2 times -1/2 minus 3. All righty, some fraction work. -1/2 times -1/2 times -1/2 is -1/8. I'm going to write this on the side. -1/2 times -1/2 times -1/2. Remember when we multiply fractions, we multiply the tops. First of all, I have a negative times a negative is a positive times another negative. I know the final answer is negative. When I multiply the tops, 1 times 1 times 1 is 1. On the bottom, 2 times 2 is 4, times 2 again is 8. So that's how that came out to be -1/8. The next one, 1/2 times 1/2 is 1/4, so it'll be 3 times 1/4. Over here we got a negative times a negative is a positive. 2 times 1/2 is just 1, and then minus 3. Here I can multiply, it's like multiplying 2 over 1 times -1 over 8. And then this is like doing 3 over 1 times 1 over 4. And it's plus 1 minus 3. So when I multiply these fractions, I get -2 over 8. When I multiply these fractions, I get 3 over 4 plus 1 minus 3. -2 over 8 reduces to -1 over 4. Now I can add these together. Remember, when I add fractions, if they have the same denominator, that's great. These do. So I keep that same denominator in my answer, and then I just add the numerators. -1 plus 3 gives me 2. Plus 1 minus 3. So then I get, that reduces to 1/2. I don't know what that is, but it's not 0. So this one did not work. So negative 1/2 does not work. We got a long way to go here. I'm not going to check all of them. I'm going to tell you that because it's a degree 3, it's got up to 3 answers. So there is one of these that works. So I'll tell you that I believe it is negative 3/2. So I want you to finish this off by plugging in negative 3/2 and see if you can get a y value. If you need to use your calculator, that's fine. I would like for you to try it without your calculator. There's a lot of fraction work in here. But if you prefer going with the calculator, that's fine. We are going to really look heavily at some fraction stuff. All right, that concludes our video.